This is a brief introduction to T-Race technology, also called T-Race, and its applications to cultural heritage conservation and investigation. Let's start considering a typical Italian Renaissance painting. This will be made of at least 3 layers: paint, gesso and wood. If we want to perform a T-ray investigation, we need 2 probes, a T-rays emitter and a T-rays receiver. The T-rays emitter sends a T-ray pulse, which reaches the first interface, air paint, let's say after 1 picosecond. The pulse is then bounced off and reaches the T-rays receiver after another 1 picosecond. A computer will display the T-ray spectrum with time in picoseconds on the x-axis and the intensity of the reflected T-rays on the y-axis. If 0 is the instant the pulse is sent, the T-ray peak will show up after 2 picoseconds. 1 picosecond for the traveling forward the interface and 1 picosecond for the traveling backward to the receiver. The fraction of the pulse which is not reflected and not absorbed by the first layer goes through the paint layers and reaches the second interface. Paint gesso. Again, the same process takes place. Part of the pulse is bounced off, reaches the receiver and shows up as a new peak on the T-ray spectrum. If the pulse takes 1 picosecond to travel to the paint, then the new peak will show up after 4 picoseconds. Same process again to reach the gesso-wood interface. If the pulse takes 1 picosecond to travel through the gesso, then the new peak will show up after 6 picoseconds. This T-ray spectrum becomes more useful if we switch to x-axis unit from time to space. 1 picosecond is 1 second divided 1 followed by 12 zeros. Speed of light is 3 by 1 followed by 11 zeros in millimeters on second. Then, in 1 picosecond, light, and therefore T-rays, travels 0.3 millimeter. We can therefore switch the x-axis from time to space, and we have a spectrum which will clearly show the actual depth of each interface. This is a T-rays application example which I developed while following conservation science at the Metropolitan Museum of Art. Object conservators and curators of French furniture were studying 5 objects attributed to an 18th century French cabinet maker, Bernard van Riesenberg. All are decorated with European imitation lacquer, so-called Japanese, and lacquered parts of Asian origin. The question was, is it possible to tell what is original Asian lacquer and what is Japanese? Since its introduction through trade from Asia to Europe in the 16th century, lacquer ware was highly appreciated and soon became a valuable collector's item. It was quickly adapted to shapes usable in a European context. This adaptation first took place with the specific orders of European customers, being executed by the Asian lacquer masters. However, at the beginning of the 18th century, these imported lacquer objects went out of fashion, though lacquer itself stayed costly and precious. It was inevitable that European cabinet makers started to reuse the lacquer objects by cutting the material into pieces and integrating them into their furniture. The high value also encouraged artisans to imitate Asian lacquer while using European materials. Fortunately, conservators had a mock-up of a Japanese lacquer which we could use to test T-rays. We wanted to prove that with a T-ray scan we could detect the lacquer substrate. Indeed, lacquer substrate could be textile, leather or bare wood. Conservators and curators were interested in a method that could tell them about the presence of the textile substrate. We brought the mock-up at the Z-Omega laboratory in Troy, New York, where it was scanned with their T-ray system Mini-Z. The mock-up shows each step of Japanese lacquer preparation from top to bottom. At Z-Omega we start collecting T-ray spectra for each step. Starting off with the bare wood, the corresponding T-ray spectrum shows only one peak, which is the reflection of the interface air wood. While the first layer of lacquer doesn't give any reflection interface detectable, the spectrum of the cloth clearly shows now two peaks, which are related to the new two interfaces, air cloth and cloth wood. The application of a coarse sand layer adds a third peak to the spectrum, and the third interface and the three interfaces are now air coarse sand cloth, and cloth wood. The application of a coarse clay layer adds a fourth peak, and the four interfaces are now air coarse clay, coarse sand cloth, and cloth wood. Polishing and fine claying don't have detectable peaks, while fine sand layers start to scatter the signal a bit. Further polishing and final lacquers do not add detectable peaks. And eventually this is the spectrum of the lacquer. Much more powerful than a single spectrum of a spot area is scanning the surface to get tomographic view of the object. We scanned a 5 by 5 mm surface of the final lacquer with pixel spacing of 50 microns. The T-ray matrix data can be shown as an area image which is similar to a photograph and presents a top-view image of the area that shows the intensity of the T-ray reflection at any desired depth. So, these images are obtained by extracting the intensity of the reflected T-ray pulses at a particular time delay or depth. Depth of 0 mm correspond to the first reflection A lacquer surface. Then we can choose to visualize deeper subsurfaces such as 0.2 mm, 0.3 mm, 0.4 mm and 0.6 mm. The only image that shows a regular pattern is the one taken at 0.4 mm. We can compare it with a macro photo of the textile, and it appears obvious that the dots on the T-ray image are spaced as the thread in the textile pattern. Therefore, the method can be used successfully in detecting the textile substrate in lacquer.